Welcome to another episode of Learn with Niloy.
Welcome to The Explainer. So today, we're taking a massive leap from pure theory straight into practice. We're going to talk about transforming artificial intelligence from this abstract, almost unpredictable kind of magic into a rigorous, highly structured engineering discipline. Because if you've ever wondered how a raw pile of data actually turns into a reliable, deployed AI application that millions of people can hit without it completely breaking, well, you are definitely in the right place. To do this, we'll be using the metaphor of a modern manufacturing factory to unpack a seriously dense 20-page technical guide on AI engineering. We're going to totally demystify the blueprint from idea to production. To make sure this is actually clear and actionable, we've organized this explainer into 6 distinct sections. First up, foundations of AI engineering. Second, models, networks, and LLMs. Third, prompting and RAG systems. Fourth, architecture, MLOps, and deployment. Fifth, security, ethics, and evaluation. And finally, Section 6, your AI engineering roadmap. Okay, let's dive into this. Section 1, Foundations of AI Engineering, laying the bedrock of our modern AI factory. The absolute core thesis of our source material is that AI engineering is fundamentally about building robust, production-ready systems. It's not just data science. It is this incredible intersection of software engineering, machine learning, data engineering, cloud computing, and MLOps. An AI engineer's job isn't just to tinker with algorithms in an isolated Jupyter notebook. No, their ultimate goal is to deliver real applications that can handle real-world traffic, scale up effortlessly, and actually recover from inevitable failures. To really understand where the engineer fits into the picture, you have to mentally separate a few terms that get thrown around a lot. You've got artificial intelligence, which is the broad, overarching field of creating intelligent machines. Inside that, you have machine learning, which focuses specifically on data-driven algorithms. And nestled deep inside that is deep learning, handling highly complex tasks using multi-layered neural networks. The AI engineer? They're the ones taking those deeply specialized algorithms and wrapping them in rock-solid, production-grade architecture. Just like a physical factory needs blueprints, specialized machinery, and raw materials, an AI engineer relies on a very specific tech stack. First up, mathematics. Linear algebra, calculus, probability. These are your blueprints. You absolutely have to understand things like gradients and matrices to know how these models actually learn. Second is the Python ecosystem. Python is essentially the heavy machinery on the factory floor, leaning on tools like NumPy, PyTorch, and LangChain. And finally, data engineering. This is your raw material pipeline. Collecting and storing data using ETL processes, feature stores, and vector databases is completely critical. Because at the end of the day, your AI is literally only as good as the data you feed it. Moving right along to Section 2, Models, Networks, and LLMs, the core AI engine. We've got the factory floor built, so now we're zooming in on the actual engine powering the whole assembly line. Every single model has to go through a rigorous step-by-step assembly line process before it ever sees production. You don't just grab a model and ship it. Step 1 is meticulously defining the problem and getting your data prepped. Step 2 is selecting the right architecture and actually training it. Step 3 is brutal validation and testing against unseen data to make sure it genuinely generalizes. And Step 4, deployment and active monitoring, because once a model is out in the wild, the real-world data it interacts with is going to shift over time, for sure. Under the hood, these engines are running on some pretty complex math. Neural networks function using perceptrons and activation functions, leaning heavily on backpropagation to learn from their mistakes. But right now, modern AI engineering is totally dominated by transformers and large language models, or LLMs. These use what are called attention mechanisms, which let the model weigh the importance of different words in a sentence no matter where they sit. You've got to understand concepts like tokenization and context windows here, because as the engineer, you are actively managing exactly how much data gets fed into this engine at any given time. All right, Section 3, Prompting and RAG systems, guiding the model. We've got our engine, but this is the critical stage where we actively drive it to get predictable outputs. Now you might be wondering, with these powerful models basically being giant autocomplete engines that love to guess, how do you actually keep them from hallucinating and securely ground them in reality? Honestly, this is probably the single most important question in modern AI application design. Well, the industry-standard architectural solution to this is RAG, or Retrieval Augmented Generation. It's a precise 4-step pipeline that tackles hallucinations directly. First, you take your trusted proprietary documents and chunk the text up. Second, you embed those chunks into mathematical vectors. Third, when a user asks a question, the system does a vector search to instantly pull the most relevant, factual chunks. And fourth, it feeds those hard facts to the model to generate a response that is securely grounded in your actual data. It completely bypasses the model's instinct to just make things up.
Alongside RAG, we heavily rely on prompt engineering. And look, scratch the idea that prompt engineering is just typing a question into a chat box. It's way more like writing a highly specific legal contract. You use system prompts to lay down the behavioral laws, few-shot prompting to give it exact examples of what you want, and chain of thought techniques to literally force the model to reason step by step. The end goal here? Highly structured, totally predictable outputs like JSON files that the rest of your software stack can reliably read and use. Let's move to and see how this builds in Section 4, Architecture, MLOps, and Deployment. Scaling to the cloud. We are officially graduating from the local laptop.
Now, what's really interesting about this setup is just how many traditional software components are required to support a single AI model. Sitting right in the center orchestration layer, the AI model is actually just one small piece of a massive puzzle. Surrounding it, you've got a front end, an API gateway catching all the user traffic. You have caching layers to speed up repetitive requests. You need vector databases for your RAG system, standard relational databases for user accounts, and a comprehensive monitoring stack. It literally takes a whole village of traditional engineering to make that one AI model useful. To keep this massive ecosystem from collapsing, we use MLOps, machine learning operations. Think of MLOps as the nervous system of your app. It handles continuous integration and continuous deployment pipelines. It maintains a strict model registry, so you know exactly which version is live right now. It involves experiment tracking, automated testing, and deep observability to catch data drift, which is when real-world data changes and suddenly your model's accuracy takes a nosedive. And obviously, you always need automated rollback strategies ready to fire the second an update breaks something. Ultimately, that nervous system relies on heavy-duty deployment infrastructure to scale. We're talking packaging applications into Docker containers so they run identically everywhere. We're orchestrating those containers with Kubernetes to handle huge, unexpected spikes in global traffic. We rely on serverless inference and smart GPU scheduling so we aren't burning cash on expensive compute power when the app is quiet. We distribute the finished product reliably and, at scale, right to the end user via REST APIs.
Section 5. Security, Ethics, and Evaluation, our quality control phase. Because absolutely no sophisticated product leaves the factory without going through rigorous safety checks.
As an AI engineer, you are constantly caught in this intense tug of war between security and speed. On one side, system defenses. You've got to lock things down against prompt injection attacks, build in strict authentication, encryption, and rate limiting. But on the exact opposite side, performance optimization. Users demand blazing fast responses. That means using tricks like caching, model quantization, and mixed precision. Nailing that balance, a completely locked down system that still feels lightning fast, is the absolute hallmark of a great AI engineer. And we don't just guess if we hit that balance. We measure it using rigorous math. We use specific evaluation metrics depending on the task. For classification, we measure accuracy, precision, and F1 scores. For generative text, we rely on things like BLEU, Rouge, or Perplexity to literally score the quality of the language. And for overall system health, we're obsessively tracking latency and throughput. You can't rely on human intuition here. You absolutely need hard data to prove the system works.
Part of proving that the system works includes responsible AI governance. A technically flawless system that's inherently biased or leaks user data, that is a total failure. True AI engineering demands strict ethical compliance. That means actively mitigating bias, ensuring fairness, building in explainability so you actually know why the model made a certain choice, and always keeping essential human oversight in the loop. Transparency is not an afterthought, it's a literal engineering requirement.
So the crucial point is, how do you actually acquire all of these skills? Let's bring this all together. Section 6. Your AI engineering roadmap, the path forward.
The source material lays out a fantastic, super clear, 4-phase chronological roadmap. Phase 1 is all about programming and data, getting incredibly comfortable with Python. Phase 2 moves you into classic machine learning and deep learning architectures. Then, Phase 3 is where you really specialize in natural language processing and modern LLMs. Finally, phase 4 is where you become a true systems architect, building RAG pipelines, deploying autonomous agents, and mastering cloud MLOps. It is a straight shot from writing basic code to full-on systems orchestration.
But here's the thing. You can't just read about this stuff. You have to start building immediately. The ecosystem evolves way too fast to sit on the sidelines. Build a basic chatbot with RAG that reads your own PDFs. Program a recommendation engine or a fraud detection script. Mess around with predictive maintenance or code up your own custom AI assistant. The absolute best way to understand the nightmare of production is to try and push a project into production yourself.
Which brings us to the end of our blueprint. Look, the AI landscape is shifting every single day. We are rapidly moving toward a future driven by multimodal models that can see and hear, and autonomous agents that take action for us. The tools are going to change, for sure, but the core discipline, building robust, reliable, and ethical systems, that stays forever. So, with this toolkit now laid out in front of you, what kind of systems will you engineer to shape that world? Thanks so much for hanging out with us on this explainer, and keep building.
Thanks for joining. Like the video and subscribe my channel to get more free tutorials.